Mhm. Hey Dave, how are you?
Oh, pretty good.
Mhm. Is today a holiday at Columbia? Maybe you don't know since you're in California.
Well, no, I'm teaching and it's not a holiday. Why are people
Yeah,
not
okay.
showing up? I see
Yeah.
5, I see 6, but for some reason they're not showing up on my video screen like they usually do.
Yeah.
Like everything is black. I mean, Zoom has been acting weird for me in other ways.
Uh-huh. Well, I see you, I see Elliot, I see myself.
I just see your black screen and I see nothing else.
There's Gordon, huh? Hi, Gordon. Huh? Long time no see.
Oh, I'm here pretty much every day, except
Yeah, but usually you're blacked
in
out.
a bad week.
Usually you're blacked out. I see your name. I don't know if you're there or not.
Oh. Well, I have no need to like not show myself there and not be there.
Okay.
It is that on Wednesdays I teach before you're done, so I have to leave early. But on Mondays I'm here.
You're here.
There's services students can buy to pretend they're in Zoom sessions in class to take attendance.
How are we doing on the time? All right, well, let's start, even though we're a small group today. So what I want to do is continue my overview of, give an outline of Serf's proof. Pseudo-isotopy implies isotopy. So let me just remind you what we did last time. So V is a closed, smooth, n-1 manifold. Eventually n is going to be greater than or equal to 6, but that's not too important right now. V is also going to be simply connected. Let's call W V cross I for convenience. And then we have the space of functions. F of V are the C infinity functions from V cross I or W into I with the following properties. F inverse of I is V cross I at the ends, I equals 0 and 1. So the bottom goes to 0, the top goes to 1, and the interior goes to the interior, and F has no critical points on the boundary. And V is going to be connected, so this actually implies that the image of V is in the, well, okay, so All right, so that's our space of functions. All functions that's in the bottom to 0, the top to 1, C infinity functions, and the interior to the interior, and have no critical points on the boundary. Then we have an important subspace. This is the F. That's it, no critical points. Okay. And the relevance of the space E to the pseudo-isotopies we showed last time, that is a map from the space of pseudo-isotopies on V into E of V, which simply sends a pseudo-isotopy to the projection on the second factor followed by the inverse of the pseudo-isotopy. So if the image of the pseudo-isotopy has these levels, these are the images of V cross T in here, then F maps the F of phi simply maps F phi inverse of I is V is phi of T is phi of V cross T. So these are the levels of this function, and because phi was a diffeomorphism, there are no critical points. And the whole purpose of this is the fibers of this map, well, the map is onto. In fact, there is a section. If you choose a metric, you can take the vector field perpendicular to the level sets and integrate it and get an inverse. The map is onto, and the fibers are orbits of the isotopy, the group of isotopies on V action, and hence connected, path connected. So we have the pseudo-isotopy space fibered, if you will, over this space of functions without critical points, and the map is onto, and the fibers are connected. So that implies that the pseudo-isotopy space is path connected if and only if E of V is path connected. That's the fibers, since the map is onto and the fibers are path connected. But P of V is path connected is equivalent to the pseudo-isotopy theorem. And because F of V is a convex subset, an open convex subset inside an affine linear submanifold of a Fréchet vector space, it's a contractible space. So F of V is contractible. All we care about is pi naught and pi 1. That implies E of V is path connected if and only if pi naught of FV EV is a single point. So to prove the pseudo-isotopy theorem, we're going to prove that the space of pseudo-isotopies is path connected. To do that, we have to prove that E of V is path connected. And to prove that, we're going to show any path in, so gamma is a path, gamma of S is a path in F of V. Gamma of 0 and gamma of 1 are in E of V, and we're going to deform this path, its endpoints, to a gamma prime in E of V. So we're going to take an arbitrary path of these functions whose endpoints are functions without critical points. And we're going to deform that path until it's a path of functions without critical points, proving the connectivity of E, hence P, and hence proving the pseudo-isotopy theorem. So that's what we did last time. Okay. So now, the way we're going to deform this path in the pseudo-isotopy in the space of functions is we're going to talk about a stratification of the space of functions. And it's only going to be important what the codimension 0, 1, and 2 strata are, since we're only dealing with points, paths, and deformations of paths. So we're only dealing with objects in the space of dimension less than or equal to 2. So we're only going to encounter generically the strata down through codimension 2 strata, which is fortunate because the actual stratification of the space is quite complicated to understand. It has a whole plethora of infinite codimension strata, which don't interest us at all. But once you get to about codimension 3 or maybe 4, the strata get quite complicated and quite hard to understand. Fortunately, we don't have to go that far. We only have to go through the 2 strata. Okay, so we're going to consider the stratification of f of v down through codimension 2. And part of that has to be that any path or any two-dimensional space mapping into f of v has an arbitrarily close approximation, and therefore homotopy map that misses everything else that I'm not going to talk about. Okay. So let me start with a very important and very elementary result that will sort of give you an idea of why things are so much simpler when we only go down to codimension 2. So suppose X is a manifold of dimension less than or equal to 2. So it's a point, an arc, circle, or a surface. And we have a continuous map. Okay. Then after an arbitrarily small deformation, call this capital Phi, Phi of X, which is a function from W, V cross I, W to R, has only Morse singularities, non-degenerate critical points, and possibly one singularity where the Hessian has nullity equal 1. Okay, so for two-dimensional families, so for points, for a single point, the generic point is a Morse function, has only Morse singularities. It turns out for an arc, the generic arcs have points with only Morse singularities, and a finite number of points with Morse singularities and one birth, which we've talked about before. Births have Hessian of nullity 1. That version remains true in codimension 2. All the singularities for all possible x's in this two-dimensional parameter space after this small deformation have singularities that only have a one-dimensional kernel for the Hessian. And in fact, there's only going to be one of them. Well, I guess that's not true. There can be one or two. Okay. But what's important here is that we're always going to work with functions where the singular points are either Morse, non-degenerate Hessians, or the Hessian has nullity 1. Okay. And the proof is a Thom transversality argument. So I think I wrote up a sort of transversality. I wrote up a quick presentation of Thom transversality, but let me show you how it works in this case. So Thom transversality is about the spaces of jets. So let's think about I need a little more room. Let's think about the first few jet spaces for maps of W into the interval. These are going to be in our class of functions, but I'm not going to worry about the boundary. Everything is fine at the boundary. It takes care of itself. So J naught is simply W, well, let's say to R instead of I. So C infinity functions from W to R. The zero jets, well, the zero jet of a function at a point is just its value at that point. So the zero jets of functions from W to R are simply pairs consisting of a point in W and a real number. Okay. These jets are stacked up. They form an inverse system. The one jets will project down to the zero jets. The one jet consists of the value of the function at a point and its differential. So in fact, the space of one jets is simply the cotangent bundle of M. That's the differential at the point cross the value at the point. And it has the obvious projection, cotangent bundle down onto W when the R comes along for the ride. So that's what a one jet is. And in here we have a very important set that we use all the time. That's the critical. So P comma T is a critical point for the jet if and only if the differential at P is 0. So this is the 0 section of the cotangent bundle. And this is just a copy of R. So you see that if I'm sorry, I'm using M. It's not M, it's W. You see if W is n-dimensional, which it is in our case, that this is a codimension in submanifold. And now the fact that the generic function is Morse is just a statement that if you have a zero manifold, namely a point, mapping into the C infinity functions of W into R, the resulting map point cross M into the jet space is transverse to this submanifold. In fact, any submanifold for generic, so this is transverse for generic choice of the point P. Okay, so that's the statement. In this special case where we're just taking our manifold mapping in as a point, we have this point mapping to the C infinity functions. That's just a C infinity function. And arbitrarily, there's a G delta of these points of C infinity functions. So the resulting map, the one jet of the resulting map is transverse to this submanifold, which is just saying that the function is Morse. Okay, so that's the way we proved that Morse functions were open dense. But now I'm going to continue and look at the two-jet space of W into R. And I want to look at pi inverse, pi 2 inverse of this Z cross R. Okay. Okay. So that's still codimension 2 because it's the pre-image under a smooth map of our codimension n, the pre-image under a smooth map of something with codimension n. So Z, the zero section of the one inside the one jets cross R, sitting inside the two jets of W to R is codimension n. But let's think about what the fiber looks like from the two jets to the one jets over the zero locus. Well, that's just, the fiber is just all possible quadratic forms. So the fiber of pi 2 over ZT is the space of symmetric two tensors on the cotangent bundle. And the map F goes to the Hessian of F at the point of F. Okay. So we've got this bigger space. The fiber of this map over any point is symmetric two tensors on the cotangent bundle. Well, symmetric two tensors on the tangent bundle. But they have canonical meaning over the zero section. Elsewhere, you'd have to choose local coordinates to get an isomorphism to symmetric matrices. But anyway, we're working over the zero locus. So what we see here is the value, that's the point in R, the differential, that's the point we get down here, and this quadratic term, which when the differential vanishes, I can identify with the Hessian. So these are symmetric forms on an n-dimensional vector space. So the dimension of Sim2 of the cotangent, I keep calling it M, it's W. Sim2 of W, well, symmetric matrices, n by n matrices, is n times n plus 1 over 2. What about those with nullity 1? So the open dense set are non-degenerate. Okay. What about nullity 1? Well, you do a simple computation and you see the codimension, it's of codimension 1. In fact, it's the kernel of the determinant from this Sim2 it's the kernel of the determinant is the space of nullity 1. But in general, it's a simple computation to show that the nullity K subspace, actually K, is a locally closed smooth submanifold of codimension K times K plus 1 over 2. Case K equals 0 gives codimension 0, an open stratum. K equals 1 gives 1 times 2 over 2, codimension 1, and this is the general formula. And one way to think about it is if you have a null space K dimensional, so here's the null space, it's K dimensional, then take a complementary space and fix a non-degenerate form here, and just add to it all possible forms on N. The zero form will give you the original one. You'll have the full symmetric forms on N, which is a space of dimension k times k plus 1. That's the transversal to this stratum, and it has that dimension. So what's important for us is nullity 2 has codimension 3. 2 times 3 over 2. And higher nullity, of course, has codimension greater than 3. So all the lower strata of symmetric forms of higher nullity are codimension 3 or higher. And therefore, when we take our map, so we have a space of dimension 1, 0, 1, or 2 mapping into the C infinity functions on M W R, I look at the resulting map of X cross W into the 2-jet space by deforming X slightly, deforming this original map slightly. I can assume that this map is transverse to any finite collection of submanifolds in any jet space. Well, I have these submanifolds in the 2 jets of lower nullity, and they're all codimension at least 3. So this map for X of dimension 2 or less generically will miss nullity 2 or higher. So now general position. I mean, let me just do the count again. So the preimage of Z cross R is codimension N. Then we have those fibers over Z cross I, which are N times N plus 1 over 2-dimensional. But then we have in the fibers a stratification, which is stratification on each fiber that fits together to give a stratification of the full preimage. And the lower strata there, well, there's the open dense set of nullity 0, and there's the codimension 1 set of nullity 1, but then you have codimension 3 for the higher nullity. So the higher nullities give a submanifold in the jet space of codimension at least N plus 3, and this is an N plus 2-dimensional manifold mapping in. Okay. So general position or time transversality implies X cross W into the 2-jet space misses critical points of nullity greater than or equal to 2. Okay. So if we apply this now not to a 2-dimensional space, but to a path, so gamma of S, let's say, is a path in our function space, and let's say its endpoints are Morse, but even more, they have no critical points. Then for a generic small perturbation, of the path gamma, and you can do this rel endpoints. The result looks like this as far as the Hessians are concerned. So here are the points in E, so they have no critical points. Then there are a finite number of values where the Hessian has nullity 1. And everywhere else, the functions are Morse. So that's what we prove, that nowhere is there nullity 2 in this path for generic path, and the nullity 1 is a codimension n+1 phenomenon. So in m cross the interval, a w cross the interval, so it will happen at only finitely many points. Okay. Now we can actually say more than just nullity 1. We can say more about the S such that gamma of S has a degenerate critical point. So not only does it have nullity 1, but it's a birth. So that's the next lemma. The nullity 1, so in a generic path, the nullity 1 points are births. And let me just remind you what that means, i.e., there is a local model with coordinates x in some Euclidean space, y in some other Euclidean space, and a one-dimensional coordinate z, and f is minus norm x squared plus norm y squared plus z cubed. I guess it's convenient to put a third. So that's the local model for a birth. Okay. So the reason for this is that we know these nullity 1 points are points when I project them. So when I take m cross I and I project to the 2 jets, I keep calling it m, should have called it m from the beginning, w cross I, and I project to the 2 jets, I have this nullity 1 subspace, which is inside pi 2 inverse of z cross r. So pi 2 inverse z cross r is simply the 2 jets with 0 differential at some point. These then are the sublocus where the 2 jet, the Hessian of the 2 jet actually has nullity 1. And what we've seen is that this is codimension n+1. This thing was codimension n, and this vanishing of the determinant gives you one more condition. So this is codimension n+1 in the jets. So I'll get a finite, by transversality, time transversality, I'll get a finite set of points in here that map into this nullity 1 Hessian. But let's go up 1 jet more from the 2 jets to the 3 jets. And I claim, if I look at the pre-image under this projection of the nullity 1 subspace, this is still codimension n+1. It has an open dense set where f is a birth of births. And let me give you an argument for that. So once I know that there's an open dense set, or in fact the complement of the stratified subspace with lower dimensional strata, finitely stratified subspace with lower dimensional strata, when I lift I cross W into here, it will miss all those lower strata, and thus these points of intersection will actually go through the open dense set of births, meaning that our singular this is the nature of our singularities at every one of these points. So recall how the Morse lemma went, about Morse lemma about canonical neighborhoods went. So the Morse lemma says if F has a non-degenerate critical point, then there are these coordinates x, y, and z, x and y, such that F is minus norm x squared plus norm y squared. And the way we did that was an inductive argument. And the argument worked as long as we were in a non-degenerate, the quadratic form on the various subspaces with non-degenerate. So in fact, that argument, in the case when the nullity is 1, shows you that you can take f of x, y, and now a single variable z to be of the form minus x squared plus y squared plus z squared h of x, y, z. So the argument actually, without assuming that the quadratic form was completely non-degenerate, only non-degenerate on an n-1 dimensional space, you got to this form. The last step in the canonical neighborhood is to say, okay, well, h at the origin, so if h 0, 0, 0 is non-zero, we can take a square root. And square root of h, or square root of absolute, I mean, epsilon, square root of the sine of h times h. So sine plus minus 1 times h to make it a positive function. And then z, a new coordinate z prime, which is z times this square root, call it phi. Phi is a new last coordinate. And with respect to z prime, you get minus norm x squared plus norm y squared plus or minus norm z prime squared, the sign here being the sine of h. So if you can take this, if h is non-zero, you can take a square root in this way and complete the Morse limit. So our problem here is when the quadratic form has nullity 1, so the quadratic form of nullity 1 implies that we're in exactly the other case, that, sorry, h of 0, 0, 0 is equal to 0. And thus we can't extract a square root and we can't complete the canonical coordinate system. Okay, but we can still do something. So if h vanishes at the origin, then that means you can write h of x, y, z as summation xi phi of x, y, z plus yj psi j of x, y, z plus z times mu of x, y, z. Using our lemma again, that if a function, smooth function vanishes at the origin, it can be written as a sum of other functions times the coordinate functions. Okay, and now plugging that back in up here, we see our expression looks like f is equal minus norm x squared plus norm y squared plus summation z squared xi phi plus z squared yj psi j plus z cubed mu, where the phi's, the size, and the mu are functions of the three variables. I guess the first one should be a sum over I, the second one should be a sum over j, and the last one is a single function. Now you do the same argument you did before. You add 1/2, so you make xi prime equal to xi minus 1/2 phi I z squared. And then when you square that, you get xi squared, maybe this should be a plus xi phi I z squared plus something that's a z to the fourth term. So when you take minus summation xi prime squared, you get minus summation xi squared. These terms exactly cancel out these, and you've added in a z to the fourth over here, so you can absorb that into the z cubed term. You do this exact same construction for the y's, and you see that you can rewrite, you can find the new coordinates, the x primes and the y primes, so that f is dropping the prime. You find new coordinates so that in these coordinates, it looks like z cubed h, maybe let's call it 3 of x, y, z. So if the quadratic expression vanishes at the origin, then you can pop in one more factor of z and get z cubed times an expression. If this expression is non-zero at the origin, you can take a cube root and find the coordinate system, and z prime equals z cube root of h3 is as required. F is minus norm x squared plus norm y squared plus z prime cubed. So that's an open condition, open dense condition, that when you solve this equation, this function is non-zero at the origin. If it is, then you have a model, which is the model for a birth. If not, that's a higher codimension condition, a lower condition, a subvariety in the 3-jet, and thus our path will generically miss that. Notice that it's very important that our nullity is codimension, our nullity is 1, because we can repeat this argument. We can keep doing this one power at a time until we arrive at a situation where we have some minus norm x squared plus norm y squared. So this is a remark. I don't need it for the argument. I've already finished the argument. Plus z to the n h n of x, y, z. We can keep doing this, upping the power of z here until this expression becomes non-zero. And each time we add one more codimension. Of course, it may be that these functions are always 0, and therefore you could keep doing this forever, and that's an infinite codimension stratum. And if you try to study what that stratum actually looks like, it's quite complicated. But we only need finite codimension strata, and we only need the first 2 or 3. So we only need to worry about z squared, z cubed, and eventually z to the fourth. But things are much more complicated when the Hessian has nullity 2. There's no simple argument like this to sort out what the strata look like. But for nullity 1, the strata just go by how large a power can you put here. Each upping the power by 1 more ups the codimension 1 more. Z squared is codimension 0, z cubed is codimension 1, z to the fourth is codimension 2, z to the fifth is codimension 3, and so on. Okay. All right. So that's a proof that as far as the singularities go, a generic path in FV, again, always assuming the endpoints are in E. No critical points. All that would really matter is that they're in the Morse functions. You get finitely many degenerate functions with degenerate critical points. Degenerate. Each x, so for each value here, Si, gamma of Si has a single degenerate critical point, and it's a birth. Okay. It's graphic, as we're going to be talking about before. If you think about the critical values, so this is the S direction, there are no critical values associated with this. There may be, of course, other critical values. Suddenly at this point, you create a degenerate critical value, and out of it grows two branches of non-degenerate critical values along a cusp. That's what a birth looks like. So there's a finite number of bursts. Of course, you can also have bursts with the other orientation, which we'll call deaths. It's where two critical points come together along and form a cusp and then die out, and they've disappeared. They don't exist after that. Okay. So that's what's happening at these points. Have to have as many birth points as death points, because you start with no critical points and you end with no critical points. All right. Furthermore, let's consider critical values with more than one critical point. So what I claim here is, this is the basic claim. If you have a function, in F, and you want to know its codimension. So it lies in some stratum. What's the codimension of that stratum? So the codimension of the stratum containing F. You look at the sum over the critical points of the codimension at the critical point of F. So take the local model for F around the critical point and ask, in the local model, what's the codimension of F? And then add in any extra agreement of critical values that, well, any extra agreement of critical values. So that would be the number of critical points minus the number of critical values. Because it's an extra condition to say two critical points agree with each other, because you're free to move the non-degenerate critical points at will. We're free to move all the critical points. They're critical values at will. So to have two coalesce and be at the same height is a codimension one condition. So in fact, I want to add now to my path other special points. Actually, I should probably call the other special points X's. So these are points where there's a critical value with two critical points in the preimage. In other words, two critical values have collided. So you have two critical values. They're distinct here. The critical value for P is bigger than that of Q on this side. You cross over and they get reversed. And at this codimension one singularity, it's still a Morse function, so it's a fairly mild singularity. The two critical values of P and Q agree. So you have codimension, you have a finite set, a codimension 1 set, where this crossing of the critical values or equality of the critical values, and you have a codimension 1 set of bursts or deaths. And so you have finitely many singularities. And what we've now shown, so F naught of V, the top stratum of V, these are Morse functions with distinct critical values. So different critical points have different critical values. F1 of V has two types, F1 V alpha, F1 V beta. So two types of components for the codimension 1 stratum. These are the bursts, and these are the crossings of Morse singularities, Morse critical points. Okay, now these sets are not themselves connected. I mean, it's sort of obvious. If you have a birth, there's an integer invariant associated to that birth, which is the index. There are two indices. The critical points that come out of a birth are index I and I plus 1. Remember, the birth had minus norm x squared plus norm y squared plus 1/3 z cubed. So you have the dimension of the x space, that turns out to be I, and then the two critical points that are born have that index and one higher index. So there are lots of different components of this stratum of bursts, or this piece of this codimension 1 stratum consisting of bursts. And likewise, when two critical points cross, you have the two indices of the critical points that are crossing. So you have lots of components here too. But anyway, that's the codimension 1 stratum. Codimension 1 stratum consists of bursts and crossings. We're going to have to talk about codimension 2, but let me first, before I do that, give you the graphic now of one of these curves. Graphic of a path in F naught union F1. So the graphic is going to take place in the square. This is an actual square. This is the parameter along the path. And this is the t coordinate in V cross I. Okay, so this square is the image of, if you project V cross I to I, that's the vertical direction. And then you have a one parameter family of functions. So the parameter value is in the horizontal direction. And what we're going to do is we're going to map we're going to take a one-dimensional graph consisting of all pairs S in the parameter space and pi 2 of a critical point of gamma S or F. Let's call these functions Fs of Fs. So if I fix S and look vertically, I get some finite set. These are the critical value. These are the critical values for Fs projected into the interval, and generically they're distinct because it's a codimension 1 condition that two of these might come together. Now, of course, this isn't all the information about the critical values. There's also their location in V, which we're ignoring for this purpose. Now, what does this graph look like? Well, since this path starts and ends inside functions with no critical points, our graph doesn't meet the edges. And since by construction of the family of functions, there are no critical points at the top or the bottom, the graph doesn't meet the top or bottom either. So the graph is contained in the interior of the square. For a while it does, as you move from s equals 0 in, for a while you don't have any critical points, and then finally you come to a birth. And then maybe the birth goes on, maybe it crosses over itself. We have another birth here. Maybe that birth cancels out this one. And then we have another, maybe we have another component here. Missing a, oh yeah, here. Maybe these things actually come together and cancel. So we get some graph that has crossing points and cusps. Each one of the arcs projects down diffeomorphically to an interval in the base, and it ends at a cusp point. And this thing is contained in the interior, unlike what I've drawn there. Don't quite have enough room. Okay. So that's our graphic. Doesn't contain all the information, but it contains a lot of information about the critical points, the bursts, the crossings, and so on. So the singular values of this path are the values of S for which there's a birth or death, and the values of S for which there's a crossing. So here's a crossing point here. Okay, and otherwise, for any other value, you just have a Morse function with critical points having different critical values. All right. So what we're going to do is we are going to make moves and simplify this graph in steps that follow in some broad sense what happens in Smale's original argument, everything being a one parameter version of that, until we get rid of the graph. So now I need to talk about the moves that we can do. And for that, let me first introduce the codimension 2 strata. There will be, well, there's one new codimension 4 singularity that we haven't seen before that's really new and occurs in codimension 4. It's called the swallowtail. And it's the functions that have a model minus norm x squared plus norm y squared plus or minus z to the 4th. So there are actually two models here. There's the swallowtail, which is with a plus sign, but there's another type of stratum with the upside down swallowtail, which is the point. Again, of course, these have codimension 1 nullity. The point here is that the cubic form now vanishes, and you get one more codimension by going to the 4th. So you have z to the 4th h4 of x, y, z. This is non-zero at the origin. h4 of 0, 0, 0 is non-zero, else we would go to codimension 5. But it has a sign, and since you're taking an even root, you get two signs depending on, so you get a sign here depending on the sign of h. So there are two swallowtails. One is right side up, the other is upside down. If you look at this stratum of a stratum of swallowtails, around it, you have a loop, and you can use that loop to change a path. So suppose this is a path in the F naught union F1 space. You can connect the path over here. Actually, I'll do it this way. Connect the path over here, go around the boundary of the link and come back out. So you change the path. It's not a deformation in F naught union F1 because you pushed the path by a homotopy across this codimension 2 stratum. That has the following effect. It takes an object like this and turns it into this. So around one side of this circle, you see a configuration like that, and you can trade this complicated configuration with a birth and a death for this simpler configuration by passing a swallowtail. The upside down swallowtail that we're not going to need, it looks like this. And as you pass the upside down swallowtail, you get that. So here are the remaining. So here you had critical points of index I and I plus 1, and the remaining one is I plus 1. Here you have I plus 1 and I, and the remaining one is I, an upside down swallowtail. So that's the new and interesting codimension 2 stratum. And I will talk about all of this in more detail later. The other codimension 2 strata come from singularities we already know about. For example, you could have 2 births at different points. So 2 birth points. That one we don't actually need. You could have a birth point and a double point. You could have a triple point. No, you can have, sorry. You could have a birth plus Morse at some level. And the other one is you could have a triple point. So birth plus Morse means you have a birth, and there's also an ordinary Morse critical point with the same value. So there's a line through the cusp of the birth. A triple point is where 3 lines come together, and that's obviously a codimension. Both of these are codimension 2 conditions. So what these codimension 2 strata let you do is the following. You might have a situation like that where you have a cusp and a line crossing the 2 singularities of the cusp near the cusp, and using the link around this codimension 2 stratum, you move to that. Or you could go the other way if you want. Here, you can have 3 crossing lines in that configuration, move to 3 crossing lines in this configuration by going around the link of this codimension 2 stratum. Okay, and there are 2 other moves that we'll use that come from the fact that if you cross a codimension 1 stratum, and then you immediately come back and cross it in the other direction, that cancels. That can be canceled. You can move this curve until it doesn't cross the stratum at all. So in terms of our graphic pictures, if this were a the crossing stratum, then we would have, these are now in our graph, we would have two arcs. They cross and then they cross again where nothing else interesting happens. And the fact that this is trivial, up and back is trivial, says you can move that to this in the graphic. And the other one, which is a little more complicated, is if you cross now a birth. So you cross a birth and then you immediately come back and cross it in the other direction. In the graphic space, so here I'm drawing paths. This is a path in F in the infinite dimensional function space, and this is a codimension 1 stratum in the infinite dimensional function space. Now I'm drawing what happens in the graph in the plane. Here you have a birth. That's this. That didn't work very well. And then you immediately, without it interacting with anything else, it becomes a death. And that you can simply remove by pushing this again until it doesn't cross the stratum at all. So those are our moves. These two require codimension 2. The swallowtail move requires codimension 2. And these two moves are an ability to cancel the crossings. And you go across the codimension 1 stratum and you come right back. Allow you to cancel, well, cancel these 2 points of intersection, or completely remove a canceling pair of birth and death with no action in the middle. If other stuff were happening here in the inside, you couldn't do that. When I draw this path, it means nothing else has happened to this critical point except the simple birth followed by death. All right, how am I doing on the time? All right. So maybe I'll finish by not trying to describe how you come up with all these pictures and moves and justifying that in fact they're legitimate. Let me just finish with the steps in, oh well, this is one more I have to tell you about. There's one more move, which is Smale's cancellation. Okay. So this is, so you have a bunch of critical points of index I. You have critical points of index I plus 1. Right. And you have a birth above the critical point of index I. So this is an I plus 1 and an I plus 2. You cross all the index I and you cancel the index I plus 1 and you cancel the highest index I critical point. So this is Smale's trading. You trade this, the effect of this is to trade an index I critical point for an index I plus 2 critical point by creating a birth, using a birth to create a pair here, and then deforming this until it cancels this critical point of index I. You know, again, you have to, when can you do that? There's, you know, various homological conditions and so on, geometric conditions, but that picture is a Smale cancellation. Okay. So the steps are, we start with an arbitrary graphic. I mean, we think of the moves in terms of what they do on the graphic, but of course those moves have to be justified in the Morse theory in the manifold, V cross I. And we make it we make it ordered. Then we concentrate critical points in two indices, adjacent indices. And then we cancel somehow. So when Smale was proving the H-cobordism theorem, this is exactly what he did, but he was talking about individual critical points. He ordered the critical points, then he, using this sort of trick, he traded up until he got all the critical points concentrated in two dimensions, and then he did his K-theory argument with matrices to show he could cancel them. Here we have to do it with graphs, with these one-dimensional objects rather than just isolated points, the critical points. So when I say a graph is ordered, if for each parameter value, each S, all non-degenerate critical points of Fs are ordered in the usual sense, meaning if P and Q are critical points, the index at P of F is less than the index Q at F, then P is below Q. Okay. So that's the definition of ordered. If a graph is ordered, you get a picture just like I was drawing up here. You have the critical points of index I, and then below it, you have the critical points of index I minus 1. And if you put in a birth creating an I and I plus 1, I minus 1 and I, that has to be done in between, at a level in between the highest I minus 1 critical point and the lowest I critical point. Because immediately after you create this birth, you're going to have a critical point of index I right here and a critical point of index I minus 1 there. So this critical point has to be above all of these, and therefore the cusp has to be above all of these. And this critical point has to be below all the ones of index I, and so the cusp has to be below the index I critical points. So when you create cusps, when you have bursts that create I and I minus 1, they have to lie in between the I minus 1 critical points and the I critical points. Similarly for death, a death can only occur when the highest critical point of index I minus 1 kills the lowest critical point of index I. So all the others have to be above it. So this condition, while it says nothing directly about the cusp, does force the cusp to be sandwiched in between the two levels where they're creating critical points. And of course, the other thing it forces is any crossing has to be critical points of index I. So crossings are only between critical points of the same index. Again, because both before and after the critical points have to be ordered. Okay, so that's what happens when we get these graphics ordered. Now, it takes a fair amount of work to get them ordered. Then we fix some integer k between 2 and n minus 3, just exactly like Smale did. And we want to concentrate all critical points of index k and k plus 1. So we use the moves, including Smale's trading move, which is crucial, and the swallowtail move. We use moves, so suppose the lowest index of a critical point is L strictly less than K. Then we use the Smale move and swallowtails, it turns out, as well as the other simpler moves, swallowtail, to trade. So here's this lowest critical point of index L, the lowest. So this is the lowest critical point of the lowest index. So it has to be born from a birth, and eventually it's going to die. And while it might not always be the lowest, by the time it dies, it has to be the lowest critical point of index L. Sorry, got that backwards. Has to be the highest critical point of index L. Well, it's the only critical point of index L when it starts, but it's eventually going to die. So maybe there are other critical points of index L that have been born. In here, I guess, actually. Eventually, this one has to be the lowest, and then it's, I don't know why I say lowest, has to be the highest. And then it will die some death because it doesn't exist all the way to the other end. So that begins to look a little bit like a swallowtail. You do a fairly intricate argument, you cancel this, you trade this arc here for an arc of critical points of index K plus, L plus 2. Okay. All right, so then you push up by induction until you reach your pre-assigned K and there are no critical points below K. Then you turn the function over and you do the same thing from the top, trading until you get down to leaving yourself only K and K plus 1. Then you have to do algebraic K theory in a way I'll explain to show you can cancel at this point. Sorry, this point. So once you have just two levels of critical points that you can cancel and becomes a K theory argument. So this follows grosso modo the outline that Smale followed. You start with an arbitrary function, you order the critical points. Here we're going to order the graph. You then start chipping away at them using Smale's trading argument to concentrate in the critical points in two adjacent indices. We do that here too. Once they're in two adjacent indices, you have to do a little algebraic K theory involving the general linear group GLQ, where Q is the rank of the homology of Z. So some K theory about this in order to show how to cancel the remaining graph. All right, so I'll start in next week on filling in the details in this argument. And with that, I'll take questions if there are any. All right, well, if there are no questions, I hope this gave you a flavor for the argument, because not surprisingly, each detail, none of them is especially deep, but some of them are fairly intricate. And so the argument will be down in the weeds from now on. But I wanted to give you what I hope is a reasonable overview of how this argument is going to go. All right. See you next week. When is Thanksgiving? It's not next week, right? Week after? So we have all of next week and then Thanksgiving's the week after?
Yes, that's right.
So I'll lecture next week. I probably won't lecture on the week of Thanksgiving unless there's giant demand for it. But we can talk about that next week. All right, see you next week.